So the last reaction for chapter 10 is about alkylating alkynes. We've seen a few different techniques for removing carbons off of molecules, right? The main one was ozonolysis, where we can cleave double bonds or triple bonds and remove a carbon group. With alkylation, we're essentially doing the opposite. We're trying to add carbons on. So let's make a note of this. It's a way of adding carbon groups to a terminal alkyne. Whoop. What does it mean when I say a terminal alkyne?
The bond at the end, so it's an H on it.
Yeah, it's got a proton coming off the end, right? The triple bond's not in between two carbon groups. There's a proton coming off of one side. So let's take a look at how we can do this. And luckily, this reaction's super simple, or at least it better be. All we need to do is remove this proton, and this proton coming off the end here has a pKa that's about 24, 25-ish. So it's relatively acidic for a carbon-hydrogen bond. That means we can deprotonate it with a strong base. And this base can come grab this proton and dump electrons on that adjacent carbon. This is referred to as our acetylide ion. And acetylide ions are really good nucleophiles. But they're also good bases. Right? It wants its proton back. So if we've got a good nucleophile, good base, I drove this into your guys' head during fall term that this can do what sort of chemistry?
S1.
Yeah, it could do SN2 or E2 chemistry, right? So in this case, we're trying to add carbons on. We're not trying to do an elimination reaction. So we probably want to do SN2 chemistry. So if we do SN2 chemistry, we've got to have some sort of electrophile with a good leaving group, something like a halogen or a tosylate. And this will do a backside attack and kick off our bromine. And by doing this, we've essentially added 2 carbons on to our molecule. Let's make a couple of notes regarding this reaction, because there's a few things that students often forget. One thing is an appropriate base. Can we use something like sodium hydroxide?
No.
No. Sodium hydroxide, its conjugate acid has a pKa of around 15. That's not good enough. You have to use a stronger base than that. The most common base that you see in the textbook is sodium amide. However, other strong bases will work as well. So typically my go-to is sodium amide. And you must use a methyl halide or a primary halide. Why can't we use secondary or tertiary alkyl halides? There's 2 reasons, right? One is the backside's way too blocked for that SN2 attack to occur on a tertiary or a secondary carbon. And the other problem is we get another reaction that occurs rather than SN2. What's that other reaction? E2. So the problem is secondary and tertiary alkyl halides do E2. So that's a little bit of review. And this is a really useful reaction, at least right now, for adding carbons onto molecules. So the main thing is anytime you see a starting material in a synthesis problem that has fewer carbons, you should think, hey, I've got to add carbons in one way or another. This is a really good way of adding carbons. We know how to make alkynes, and we know how to manipulate them. So this is a really valuable tool that we have. All right, so what we're going to do is we're going to spend the,
How do you prevent that protonation from reoccurring in one other direction?
once you have your acetylide ion.
Yeah.
So remember, this is really just an acid-base equilibrium reaction. So as long as your base is strong enough, it'll stay at that acetylide ion side and won't favor going back to the starting material. However, with a weak base, you're right, you would reprotonate it and it would go right back to the starting material side. All right, so with the rest of the class period, what we're going to do is we're going to take the big sheets of paper that we have, and we're going to make something called a reaction map. Has anybody seen or heard of a reaction map? Okay, I'll show you guys what I mean by a reaction map. And a reaction map can be however you guys want it, but it's a good visual way of kind of organizing all of your thoughts and ideas throughout organic chemistry. Oh. And a reaction map basically consists of a bunch of functional groups being connected by arrows, right? So for example, for my reaction map, I'm going to do a bunch of halogens on one side. I wouldn't write anything down on your map right now. You're welcome to use my template if you want, but you don't have to. Oops. So we've got some halogenated compounds, got some tetrahalogenated compounds right here, and then over here I'll add in more halogenated compounds for fun. These are all of the different ways we know of adding halogens onto compounds in multiple ways. And then we've got some alkynes. And we know we can make a bunch of stuff from alkenes. I'm purposely making my alkene neither cis nor trans. I'll let you guys make notes or add in both cis and trans alkenes if you want. I'll add in some alkanes here. I'll add in some alkyl halides or tosylates. Those are things that have good leaving groups. And then we've got another one where we've got an alcohol and a halogen. We've got ones where we have two alcohols. And again, I'm not even including stereochemistry right now. And we could have one with an epoxide, and we could have one with an alcohol. Your task is to connect this with as many different arrows as possible. So, for example, how can we get from an alkyne to an alkane? How do we go from triple bonds to single bonds? H2 and palladium or platinum. Okay. How can we go from...
Well, wouldn't you have to do ozonolysis? Because if you just make it...
Well, let's just...
carbon ring.
Right now I'm not showing the true number of carbons. We're just focusing on functional group transformation. But let's just try adding to this, right? So how can you go from an alkyne to an alkene? Yeah, H2 and Lindlers. And then oftentimes what I do with my reaction map is I try to make some side notes, right? So H2 Lindlers means I'm getting what alkene? Cis or trans? So I'll make for cis under here. And then under here I'll say, all right, what's the other way of making an alkene?
Solving thing.
So you could do a dissolving metal reduction and then make a note that says for trans. So I'll let you guys organize this as much as you want. But one thing I would do is spread this out across your page. Try to give yourself more room than you think you need, because you may want to add in more arrows as you go along. This is entirely for you. It's not something I'm going to collect. But what I recommend doing is hanging on to it And then anytime we're doing a synthesis problem, you can pull it out of your binder and you can use it for your synthesis problems. Obviously not on an exam, but it's really helpful for pods and things like that. So what I recommend doing is push some tables together. I've got extra scratch paper, so if you mess up, you're welcome to start over again. But this is a really valuable exercise as we're going through the term to add in more and more functional groups and try to connect your highway map.